All right, let's do this question. It says find I1 and VO in the circuit. So they give us a circuit diagram and they want us to find the current I1, which is the current through this resistor, and the voltage VO, which is the voltage across these two terminals, which we know is going to be the same voltage across this 4K resistor. All right, now the first thing I'm going to do is I'm just going to start to simplify this circuit diagram, because the easiest circuit to work with is going to be a series circuit with one source, whether that's a voltage or a current source, and one resistor. It can be 2 or 3 resistors as well, but the best circuit to work with. Now when I look at this circuit diagram, I know we have resistors that can be combined. So remember, anytime you can combine resistors to make your circuit diagram more simpler, you should do that, right? So when I look at this, I have a 2K and a 4K resistor that's going to be in series. So because these resistors are in series, I'm just going to add these two resistors. 2 plus 4 is going to give me 6. So let me write that down. We have 2K plus 4K. That's going to give me 6 kilo ohm. I'm going to redraw this circuit diagram. And we know the value of this resistor is just going to be 6K. Now, don't forget, we have the current I1, which is through this resistor here. We didn't touch this resistor, which means the current I1 is still going to be flowing through this resistor here. I'm just going to label it I1. Now think about it, right? We had a voltage VO here through these two terminals. Once we combined these two resistors, even though that this 4K had the voltage VO, because these two resistors are in series, they do not share the same voltage. So once we combine these two resistors that are in series, the voltage VO is no longer there. But what is still going to be there is going to be the current, right? So think about it. Current is going to leave this source, right? When it leaves this source, it's going to come this way. And we can call this current I sub 0. Once this current I sub 0 reaches this node, it has two paths. It can go in this direction, which we label that current to be I1, and it can go in this direction, I2. So the current I2, which flows through the 2K and the 4K, is still going to be remained when we combine these two resistors that are in series. So we can draw a current I2. Okay, now we can simplify this further. We know the 12K and the 6K resistors are going to be in parallel. So when we combine these resistors, we're going to have 4K ohm. So our equivalent resistance is going to be 4K. Now that we know that, let's redraw this circuit one more time. We know this is 6 volts, and the equivalent resistance is going to be 4K. Now think about it, right? The current IO is still going to be in the newly drawn circuit. So we're still going to have IO, but because the current doesn't have two paths to travel, the current IO is actually going to go all the way around this circuit. Which means the current IO is the same here, and the current through this resistor is also going to be IO. Therefore, we can find the current IO by using Ohm's law. So let's use Ohm's law to find IO. We can say IO equals voltage over the resistance. The voltage is going to be 6 volts over 4K, which is 4,000. When you put that in your calculator, IO is going to equal 1.5 milliamp. Now this isn't your answer because they want you to find I1, but this can possibly help us to find I1. So let's just circle this for now. Alright, so now that we have solved the voltage and the current, and we know the resistance in this particular circuit, let's look back up to this circuit now, right? Remember, they want us to find I1. Now there are multiple ways you can solve for I1. You can take a KVL loop at loop 1, or you can just do current division. I'm just going to use current division for the sake of practice. So when I look at this, I know this current, which is the source current, is going to be I0, and we just found that to be 1.5 milliamp. Therefore, I can write a current division equation to calculate for I1. I can say I1 equals IS, which is I source, multiplied by R2 over R1 plus R2, right? We know I1 is what they want us to find. I'm just going to write it back. So I1 equals the current source. I know the current source is going to be represented by what I labeled as I0, which we just found as 1.5 milliamp. I can write this as 1.5 times 10 to the minus 3, close bracket, multiplied by R2, which is going to be the resistor opposite the current in I1. So that's going to be 6K. So we're going to have a 6,000 resistor over R1 plus R2. That's going to be a 12K plus 6K. So we're going to have 12,000 plus 6,000. Let's start to simplify this. We're going to get I1 equals 1.5 times 10 to the minus 3. Now when you simplify this, you're going to get 1 over 3. So when you multiply these two, you're going to get I1 equals 5 times 10 to the minus 4 amps. Therefore, we can write this as I1 equals 0.5 milliamp. Our answer for I1 is going to be 0.5 milliamp. Okay. All right, so let's solve for VO, right? We know VO is going to be the voltage across this resistor here. Well, when we look at this now, we have options. We can do KVL at this loop. We can use Ohm's law, find the current in I2, and then once we find the current in I2 multiplied by this 4K, you can take the KVL at the big loop to find I2 and then use that to find the 4K. So there are multiple ways you can solve this problem. You can either take a KVL loop for loop 2 and you should be able to find the voltage in this 4K resistor. Now what I'm going to do is I'm just going to use KVL. I think it's good practice. So I'm just going to use KVL, right? And I know the voltage VO is going to be just across this resistor. So we cannot use this 6K to calculate the voltage VO because the voltage is only parallel to this 4K, which means it's only the same in this 4K resistor. Now when I look at this, like I said, I think I'm going to use KVL just for the sake of practice. So I'm going to take KVL at loop 2. Alright, so when I take KVL at loop 2, we must be able to have polarities. We don't have any polarities, so I'm just going to add in my polarities, right? Because the current is flowing downwards, I'm going to assume that the polarity is going to be plus to minus, right? Also, I'm going to assume the polarity of this resistor is going to be a voltage drop plus to minus. So let's start to take KVL at loop 2. We're going to go into the negative terminal for this 12K resistor, but we don't know the voltage, but we know voltage equals IR. So we can say 12K times the current, which is I1. So let me start to write this out. You have KVL at loop 2. We have negative I1 multiplied by this 12K resistor. I'm just going to write 12K for now. Then as we continue to travel around this path, we're going to run into the positive terminal, and it's going to be plus I2 times 2K. So we're going to say plus I2, and that's a 2K resistor, once we come around, we know we're going to be entering the positive terminal, so it's going to be plus, the current is going to be I2 times 4K. So we have plus I2 times 4K. And we know all of this is going to equal 0. I'm just going to move it down. So this equals 0. Alright, so let's start to simplify this. We know the value of I1 is 0.5 milliamp. So we can substitute that in. We can say minus 0.5 times 10 to the minus 3 multiplied by 12,000, which is the 12K resistor, plus we have I2 plus I2. And because we have I2 for both of these, we can just add the resistors. So we're going to have 4,000 plus 2,000. That's going to give us 6,000. I2 equals 0. We want to find for I2, right? So when we multiply this out, we're going to get, this is going to give us negative 6 plus 6,000. I2 equals 0. We can say 6,000. I2 equals positive 6. We're going to divide both sides by 6,000. These two are going to cancel out. Therefore, you're going to be left with I2 equaling 1 milliamp. And this is something we should actually expect, right? Because the current leaving this particular source is 1.5 milliamp. We know the current through this branch is 0.5, which means there's only going to be 1 milliamp of current flowing this way. I just did it for the sake of practice with KVL, and just to show you there are so many different ways to solve these problems, right? So I know I2 is 1 milliamp. So to find the voltage VO, I'm just going to use Ohm's law. I can say VO equals IR. We know that current is going to be what I labeled as I2 times the resistance, which is 4K. I'm going to write 4,000. And we simplify this. I2 equals 1 milliamp, which is 1 times 10 to the minus 3 multiplied by 4,000. Therefore, when you solve for this, VO is going to equal 4 volts. So this is going to be your answer for the voltage across the 4K resistor. So as you see, we have successfully solved this problem. We used various methods to solve these problems. The first method we used was, we noticed these two resistors were in series. So we used the method for resistors in series. We added these resistors. Then we noticed that these two resistors were in parallel. So we combined these resistors in parallel. We was able to find the current IO, or the current source, by using Ohm's law. Once we have that, we used current division to find the current I1. Then once we did that, we used KVL to find the current I2, and we used Ohm's law to find the voltage VO. So there are many ways you can solve these problems, like I said earlier. The thing is, once we practice these different things, consider them tools in your tool bag, right? You can take them out and use them as you like. You don't have to, for example, if you have a hammer and a mallet, right? You can use a hammer to bam nails, but you can also use a mallet to bam nails. It's really up to you which one you want to use. They can both get the job done. One way might be more easier than another way, but the only way to really be able to know right away is just to keep practicing and being good at all of the techniques, because you never know when you might need a particular technique. So this is it for this video. Stay tuned for more examples.